talking about heat transfer. We really had all of these, just these two Q's, the MC delta T, and the Q is equal to plus or minus ML. That in-class assignment that we did during lab took some of you almost an hour. It shouldn't take you that long, but it's good that you took the time to work through it. I want you to realize that that is a very good example over the physics. The math was a little bit long. That could have been a lot easier if I asked you to solve for anything other than the T that was inside the delta T. Okay? The part that you need to focus on those is really anytime you have those phase diagrams or a phase change, you really need to draw the diagram and figure out where you are on the diagram. We have three different C's. There's a C1, a C2, or a C3, or whatever you want to call it for the different phases there. And we saw that with the phase diagram example we did in class. Some of you made the mistake of, for water, this was 2100 joules per kilogram per degree Celsius there when it's in the form of ice. And then it was 4186 joules per kilogram per degree Celsius over here. Okay. I gave you a problem where we started at 0 degrees, which is at the melting point here, and so you went along this part right here of this path, and then you went up a little bit up here to go up to some equilibrium temperature for the fluid in that container. But remember that you have all these parts here, and you really should just be thinking about where are you on the phase diagram. If you're already at the temperature where you have a phase change, then you start in there and then you work with that part, then you had to heat up that melted ice. If I gave you ice that was below 0, you would be down here, you would warm it up some with that specific heat, then you would melt it, then maybe you'd raise the temperature again, so you could have 3 different Qs just for those ice cubes. Then we still have the fluid in the container and the container itself. Okay? So this is one thing where we had 4 different Qs on that problem on the in-class assignment. And the math was a little bit long because you had to expand out the delta T's and then distribute and solve. But the sum of the Q's being 0 and getting Q1 plus Q2 plus Q3 and Q4, all the physics is right here in this equation. If you miss any of these Q's, this is a huge mistake. You lose a lot more points for missing something here than you would have lost for having trouble factoring out something down at the bottom once you put them in there. So, and this is the part here that, sometimes I give you these harder examples and you think, well, maybe that won't be on the exam. We had the same thing with one of those problems where we had, I think, a pulley system with the mass on an incline and a spring that was very hard on the homework because it turned out to be quadratic. But then I gave you a very similar problem on the exam with a mass and a spring on an incline. And as long as I don't ask you to solve for the variable that is quadratic, the physics is basically identical and you're solving for a different variable. So go back and review this, make sure you understand how to set these up. Make sure you can think about how this would work if I was starting with ice that was below 0. And use that same kind of procedure when you're summing up the Q's for any of your heat transfer problems. The majority of this last homework set is about kind of using these Q's here. There's not going to be any new big equations today. It's really a lot about this here in that homework. So get that started if you haven't yet. That'll be due next week. We're going to do one more now, talking about converting that heat, or converting mechanical energy, into heat energy. So I kind of just mentioned that last time, how I could take, a small stone or something, drop it from a very high cliff into a pond below, and that object that we drop, the stone or whatever it may be, has energy. It has potential up here, it has kinetic, so it hits the ground or hits the water down below, and that can hit the ground and transfer some of the energy into heat energy, and then that would warm up the water below. We're going to do a problem now, the last one on our handout from last time, with a bullet hitting a target, and then melting on impact. And that's just going to be a conversion of what we call mechanical energy, the kinetic and potential energies that we already know about, into heat energy, these kind of Q's we've been learning about this week. So This is heat energy, mechanical energy, or mechanical work, things that are related to mechanical energy, are all the forms of energy we've learned about before. Really just kinetic and potential energy. We have K is equal to 1/2 mv squared. We have U, gravitational potential energy, is mgy. We also have U for a spring, elastic potential energy, but I'm not going to write that down now because we're not going to use it. But these are the forms of energy that we know about before, or that we learned about back in Unit 3. Okay. So on this problem, and this is objective number 13. You want to kind of check that out on your objectives, which just says to use conservation of energy to determine the change in temperature of a system when mechanical work is done. Mechanical work is just related to changing any of these forms of energy right here. And this is for things like, an object that falls into some water down below, heating it up, or a bullet here hitting a target and melting. Something where you have an object in motion, something with mechanical energy, and somehow that's going to be converted into heat via friction. In this case here, when the bullet's going to strike a target. Okay. So it said here that if a lead bullet's going fast enough, it can melt completely on impact. Okay. All of its kinetic energy is going to be converted into heat via friction. This won't always be 100% of the energy being converted into heat, but sometimes it's less, and we tell you maybe only 75% of it is converted into heat, or a certain percentage is used to heat it up or warm the water when something falls into an ocean, a lake, whatever it may be. Okay. So we're going to heat up a bullet, melt it completely when this bullet hits a target and stops. We want to find how fast that bullet, the minimum speed, how fast the bullet needs to be going for that to happen. So find the minimum speed of this lead bullet so that when it hits a target, and comes to a halt, it melts completely. These are all about converting these forms of energy into these forms over here, the Qs. Okay. What kind of energy does the bullet have before it hits the target? What kind of potential energy? What kind of potentials do we know about? We have potential energy due to what two forces? Gravity and spring. So those are the only two equations we have potential for. This was for gravity here. And I'll write it down now that we mentioned it, but for a spring, these were the only 1/2 kx squared for a spring. The bullet is doing what before it hits the target? It's moving. So what kind of energy do we have for motion? Kinetic energy. If I was saying that I was going to shoot the bullet up at a target vertically or down, I could say that it has potential energy. But we can also choose our potential energy to be zero anywhere we want to, right? We could also choose our ground to be anywhere. So even if I'm assuming we're going to shoot the bullet horizontally just because that's the way that I imagine it. But if I wasn't imagining it that way and I'm saying, well, maybe I'm going to shoot it straight up or straight down, then I could say, well, it's up in the air, it's above the ground. Remember, we asked ourselves, is it moving? Is it above the ground? All those kind of things over here. But either way here, I would probably say that wherever the bullet's going to collide with the target, I'm going to let that be my lowest point on my gravitational zero, so we won't have any potential energy. Okay. So we know the bullet's going to be moving, it has kinetic energy. Then it hits the target, stops, and the friction heats it up and melts it completely. What kind of energy is that going to be up here? It's going to melt, right? So that's a phase change. Okay. These are things that you should be thinking about when you're thinking about these energy problems now. It's just new forms of energy with the Q. This will be recognizable. When something's moving, you're going to know you're going to have these kinds of energy here. And these will be different, or they should feel very different than the problems that we did where we're just simply melting ice or putting ice into a container there's going to be something in motion with these. Okay? Or maybe something won't feel like it's in motion in this statement of the problem, but I might say that I have something here and I drop it, so it will be moving when you let it go. But there's going to be something related to motion with these conversions of mechanical energy into heat. So you just really decide what kinds of energy you have. I'm going to put all these together and basically say that energy is conserved. Which it is, because there's going to be no external force that's doing work. Right? If there was some work done, then we wouldn't have energy conservation. But you might remember this equation. The initial plus the work is equal to the final. And that's just saying, as long as there's no work done, the energy is conserved. Basically what we're doing is taking mechanical energy and saying it's going to be equal to heat energy. Because we're just going to be converting from one form to the other here. The mechanical energy is this stuff over here, which will usually be in the form of kinetic energy for these problems. And the heat energy is just all of our Q's. So we're really going to have here 1/2 mv squared for the kinetic energy of the bullet before it strikes the target. Then it heats up and melts over here, so we're going to have Q's over here. We said we have a phase change here. What should we draw every time we have a problem with the phase change? A phase diagram to make sure that we account for all the possibilities of different Q's that you might have. Because when you go through a phase change, depending on where you're at on this diagram, if I start down here and I need to go all the way up here, then I got a bunch of different Q's to go through before I can even get to the point up here. That's why I've always said draw this and decide where you are on the phase diagram so that you know what Q's you have to account for. Okay. So if this is lead, you should all be able to draw me the phase diagram for lead. And I say, okay, draw the diagram, label the axes, the significant temperatures, and the different phases and processes in the diagram. So that was kind of one of our objectives. You should be able to sketch this, and if I tell you what it is, you should be able to label some important things on here. So what would go right here at that point? This would be the melting point. And what number would that be? How would we find that?
Table in the book.
So you just look up the table in the book, and there's not a special table for melting points, but it's all in the table with the latent heats. You have your melting points and your boiling points. So if you have that table handy, just get comfortable reading through it, and I'll give you the numbers here, but you need to at some point look at that table so that you're not just seeing it for the first time on the exam. It might be nice if your eyes have seen that before. But we can look these up where we have a melting point here, 328, so you could label that down at this point over here. And then, what about the other one? Up here. What would I put up there? The boiling point, which is what number?
1,764.
Okay, so if you have numbers, you can just put those numbers on there. I'm kind of putting the words in the number here just to remind us of what these are, but we should definitely be able to label those temperatures when we know what it is. And then always label, this is your temperature axis. Now, if you are just sketching this for yourself to do a problem, you don't need to label it carefully like I'm doing down here. This is Q in joules. And you don't have to put all the words on here for the solid, the liquid, and the gas, and the phase changes and all that. But if you're just doing it for yourself for a problem where I don't ask for it, just sketch it, put the numbers on there where they need to be if you need that number, and understand the diagram. Okay? Don't worry about labeling it all unless I ask you on that question to draw a complete phase diagram with it labeled. Okay? So I'm going to leave some things on here. But the reason we're doing this for any phase change problem is to make sure that I don't simply just say I want to melt the bullet and only do this Q right here. Because that by itself isn't always going to be enough. What temperature is the bullet before it hits the target?
It's a solid.
is a solid, and what temperature is it at? I think we gave you that.
328.
Okay, so that's what you need to be thinking about. Our initial temperature is 30 degrees Celsius for the bullet, okay? So where are we on the phase diagram? In the solid phase over here, somewhere over here, maybe at a point right there. And you can even label that point here if you want to at 30 degrees Celsius, okay? You have to go over this part right here before you get here. I can't just jump straight to there. So we're going to have a cue for that part. Where is the melting of the bullet going to occur on the diagram?
320 degrees.
At that point and on this horizontal segment of the graph. So here is where the bullet melts. Okay. And the bullet's going to melt completely. If you're completely melting something, then it goes all the way across the whole thing. If you only did part of it, then you may not have this whole entire segment right here. You might only have a piece of it, because you wouldn't have enough energy to melt the whole bullet, or to melt all the ice, or whatever it is. But these are the two parts on the diagram that we're having to go through here to completely melt that bullet. Make sure you don't forget this part. This would be a huge mistake on a problem like this, to forget one of the cues. Once you know this, as long as this is clear, all we have are these two cues right here. Temperature changes and phase changes. When we're going that way on the diagram, we have positive cue for this one. Remember, you choose the sign on these based on the direction that you're going in, whether you had to input heat or remove heat. And then you just need to account for both of those. This is really then just going to be the ML, and that's LF for the latent heat of fusion there, which we can look that up also, plus the MC delta T. So let's get some numbers here for specific heats. The C is 130 joules per kilogram per degree Celsius. The latent heat of fusion is 0.25 times 10 to the 5th joules per kilogram. So make sure you're always dealing with temperatures in Celsius when you're doing these heats due to temperature changes. You can remind yourself of that by just simply looking at the units of all your specific heats. That'll remind you, hopefully, to be using temperatures in Celsius. That's it. This kinetic energy is being converted into heat energy here. All of it is being used to convert into heat, so we don't have any factor here of a percentage or anything. Plug all the things in here, solve for V, I think we know, the L, the C. What's our delta T here? How do we find that? What's my T final?
328.
Yeah, because we're at the melting point. And then our delta T would be this minus 30, so we're at 298. And that's positive because we're doing final minus initial. What are all these masses?
Doesn't matter.
Are they the same?
Yeah.
Okay. Would they be the same if I was dropping a rock into a pond? This over here would be heating up the water. This over here would be the rock that's falling. So these won't always be the same mass. They are on this problem because what's moving is the bullet and what's melting and changing temperature is the bullet. So you know how I said that this won't always be 100% of the energy going into heat or heat for the bullet? This is saying all of the kinetic energy is converted into heat for the bullet. Do you think that's really true? Where else does some of that heat go? To the surroundings, to the target? But most of it goes here, we're assuming here 100% does. But in situations where we tell you that there's only 70%, then there's some of that energy that goes into doing other things. Okay? Here, it says 100% though, so you just use it that way.
If it said 70%, wouldn't you just find the 100%?
Yeah, just put 70% of this, 0.7 times that, and I think you'll have some on the homework where it might say something like that, that only 70% goes into heat, and you just put that percentage in here. or find, the thing that you may not be able to do those, you might not be able to find what the 100% is. We can't always get numbers, so just know how to write it as 0.7 times this, or 70% of that, whatever the number would be. Okay? But here, yeah, we can divide out all these masses. We have V would then be equal to 2 times the latent heat of fusion, plus the C, and times the delta T here. Take your square root, and just plug our numbers in now, you got it. So V is equal to 2 times the L here. And let's add on C times the delta T. Do you think this number is going to be big or small for the speed of a bullet? Big. Something not 5 meters per second, right? Something that would be logical here for the speed of a bullet. You get 357 here for that speed.
So faster than the speed of sound?
No.
Speed of sound in the air was 34.
Oh, this being fast, yeah. Yeah. The 343 that we're using in the lab is the speed of sound in there.
I have a question. Where did we get to the 130?
From the table. Specific heat for lead.
Okay.
Did I write the wrong number down?
No, I just didn't realize that.
Okay.
I think it's like, it's the one on page 390.
Yeah, and all those tables, we have 4 or 5 now throughout this unit that I can use. I've been kind of looking at this sheet that I've shown you here that I use in class that has, I've got 5 different tables on here and then some other constants over here. But I usually just give you the same sheet here. These are all straight from your book, so you'll know exactly what they look like. They won't look any different than what you see there in your book.
Have you decided if you're gonna give us the volume equations yet?
Yes, he has.
It's a yes. See it.
Yes.
Probably. I probably won't give this to you until Tuesday, the equation sheet or the constant sheet, but I will show this to you, or whichever one I'm going to give to you that week. As of right now, I have some other equations out here that I'll probably give you also. I usually give you some of these just because they're older in case you forgot. With these questions on the exam about mechanical energy and heat, they don't change that much. Here it was a bullet, it could have been something else. It could have been a rock falling into a pond below. But there's going to be something with motion, so something that had potential or kinetic energy going into heat, and you will either be just simply raising the temperature or maybe raising the temperature and changing the phase of something. But it's just going to be in the form of usually these two being equal. There may not be 100% of the mechanical energy, but they're going to set up like this. There will be a question on the exam where we're using kind of this relationship here between mechanical energy and heat energy. That will be one question by itself that puts these things together. I've already told you on the objectives that numbers 12, or 11, 12, and 15 were kind of really all about calorimetry, this equation for a temperature change and this equation for a phase change. There aren't separate problems on 11, 12, and 15. Those are just all about our cues. Okay, we're using those cues in this process. I'm telling you, there will definitely be one question where we have this in there. There will be other questions that have these cues in there, but they may just all be in the same problem like we saw with that in-class assignment last time. And that did calorimetry, it did phase change, it did temperature change, all in the same problem. Those are all about the cues that you see there for those 3 objectives there. The phase change diagram or the phase diagram is 14. That's going to be a question where I have you draw that and label it completely. The Number 10, define the kilocalorie, that's just a simple, short definition question that I'll put on there. But yeah, it was those 11, 12, and 15 that kind of get mixed in together. Okay. Number 16 says to define the 3 methods of heat transfer. I've got a picture or two to show you up here, so I'm just gonna pull these up.